Welcome to this video lecture on backtracking and solving n-queens problem using backtracking. Materials in this lecture are taken from the prescribed textbook Computer Algorithms by Horowitz, Sani and Rajasekharan. Backtracking is an algorithmic design technique like divide and conquer, greedy method and dynamic programming. Backtracking is used to solve problems with a combinatorially large solution space, problems that require to satisfy a set of constraints. The problem defines normally what are the constraints to be satisfied. This is also referred to as CSP, constraint satisfaction problem. And normally the problems which we solve by backtracking may have one solution or more than one solution. Optionally, backtracking is also used to solve a class of problems in which maximization or minimization of an objective function is involved. To make you understand, problems like finding the minimum cost of a tour of a traveling salesman problem or maximizing the profit in a 0-1 knapsack problem belong to this category. However, in this lecture, we limit ourselves to problems which have large solution space, which satisfy a set of constraints, and which may have a solution or more than one solution. We do not address problems with maximization or minimization of an objective function. The solution is often expressed in the form of an n-tuple x1, x2, xn. And when it comes to the implementation of the backtracking algorithms is very naturally done by making use of recursion. Now let's look at all these aspects of backtracking with the help of an example. A classic application that is used, that solved using backtracking is an n-queen problem. Now let's take an instance of an n-queen problem where n equal to 8, that is 8 queens problem. The statement of the 8 queens problem goes like this. You are given a chessboard of size 8 by 8 and you are given 8 queens, and the problem requires that you should place these 8 queens in such a way that no 2 queens attack each other. So you have to basically find a placement of the queens, positions of the queens, such that no 2 queens placed on the chessboard will attack each other. This graphic should illustrate the statement of the problem further. We have an 8 by 8 chessboard here. 8 queens are already placed. And if you look at the placement, no 2 queens attack each other. For example, the first queen is placed obviously in the first row, is in the column 4. The second queen, which is in the second row, is placed in the column 6. The third queen is placed in column 8. Similarly, the other queens are kept in their respective columns. Now let's see whether any 2 queens attack each other. Before we look at that, let's see what's meant by 2 queens attacking each other. Those who are familiar with chess should be knowing that 2 queens will be under attack if they are in the same row or if they are in the same column, or if they are in the same diagonal. I repeat, two queens are under attack if they are in the same row, or if they are in the same column, or if they are in the same diagonal. So if you look at any two queens in this graphic, they are neither in the same row, nor in the same column, nor in the same diagonal. For example, the first queen, which is placed in the first row, is in column 4, and no other queen is placed in the column 4. And of course, no other queen is placed in the first row. And if you look at these diagonals, no queen is placed in the diagonal that is placed in which the first queen is placed. And in this diagonal also, if you see, no queen is placed. This holds good for any combination of two queens. If you take any two queens, the conditions that are to be satisfied will hold good. And hence, this is a valid placement of 8 queens on the 8 by 8 chessboard. How to express the solution? Solution can be expressed as 4, 6, 8, 2, 7, 1, 3, and 5. It's an 8 tuple where each value represents the column in which the respective queen is placed. The first column value corresponds to the first queen, the second column value corresponds to the second queen, the third column value corresponds to the third queen, and so on. Let's look at some of the notations that we are going to use in this lecture. We know that two queens cannot be placed in the same row. So all the 8 queens should be placed in the 8 different rows. So the first queen placed in the first row, second queen is placed in the second row, the third queen is placed in the third row. Or the other way around, the queen placed in the first row will be referred as first queen, queen 1. The queen placed in the second row is referred as the second queen or queen 2. And similarly, the queen placed in the sixth row is referred as sixth queen or queen 6. Now, each queen is placed in a row, and suppose consider this queen which is placed in the fourth row. So the value of I is 4, where I represents the row in which the queen is placed. So because this queen is placed in the fourth row, obviously this is the fourth queen. The other way of looking at this queen is it is the fourth queen. Now the column in which this queen is placed is 2, and hence xi, that is x4, is equal to 2. x4 equal to 2 means the fourth queen which is placed in the fourth row is in the second column of the fourth row. Similarly, here the value of j is 7, and hence the position of this queen, the column position of this queen, xj, that is x7, is 6. x7 equal to 6 means that the 7th queen or queen 7, which is obviously placed in row 7, is in column 6. So this is the notation what we normally follow. xi represents the column in which the queen I is placed obviously in row I. Now let's try to enumerate the solution space, because initially we said backtracking is used to solve problems with a large solution space. Now if you observe the placement what we have seen in the previous slide, The first queen can be placed in one of the 8 squares, in one of the 8 columns. So the first queen can be placed in 8 positions. Once the first queen is placed in one of the columns, this column cannot be used to place any other queen. And hence, the second queen can be placed in 7 columns, one of the 7 columns, any one of the 7 columns. Of course, for the time being, I am ignoring the diagonal constraints. I am only looking at the row and column constraints. We are trying to make a simple enumeration. The third queen can be placed in one of the 6 columns because 2 columns are already reserved for the first and second queens. So if I continue like this, I realize that the first queen can be placed in 8 positions, the second queen can be placed in 7 positions, third queen can be placed in 6 positions, and so on. And hence, what are the possible position combinations in which 8 queens can be placed? And that defines the size of the solution space. So obviously the size of the solution space here is 8 into 7 into 6 into 5 into 4 into 3 into 2 into 1, which means the size of the solution space is 8 factorial, or there are 8 factorial possible tuples, 8 tuples. 8 factorial possible tuples are there, which are candidates for being the solutions. However, all of them cannot be the solutions. Only few of them will satisfy the constraints and can be the solutions. But otherwise, there are 8 factorial possible tuples which can become the solutions. Hence, we say that the size of the solution space is 8 factorial, which is a very huge number, and backtracking is best used to solve such problems where the solution space is very large. It's very huge. And of course, as we said earlier, there can be more than one possible placement of the 8 queens. So it may have more than one solution. Now, how to represent the solution space? Solution space is very huge. So if you want to work on the solution space, if you want to find the solution, you have to very disciplinedly work on this solution space. Not only work on the solution space, before you work on the solution space, you should organize the solution space. You should find out the right data structure to organize the solution space. Now, because 8 queen problem is very big and it's having a very huge solution space, to understand the things in a better way, let's consider the 4 queen problem where the solution space is small and it can be better handled to understand things. Now the solution space consists of 4 factorial tuples, 4 into 3 into 2 into 1, 24 possible tuples. These are all the possible tuples corresponding to the placement of 4 queens. 1, 2, 3, 4 is one possible tuple. That is, the first queen is placed in the first column, second queen is placed in the second column, the third queen is placed in the third column, and the fourth queen is placed in the fourth column. If you look at this tuple, the first queen is placed in the third column, the second queen is placed in the second column, the third queen is placed in the fourth column, and the fourth queen is placed in the first column. So we see that there are 24 possible tuples, and they can be organized as a list of tuples. So list is a data structure in which you can organize the elements. So you can regard all these possible candidates that comprise the solution space be organized as a list. Is there any other possible organization of the solution space? Yes, there is another possible organization of the solution space which is more amenable for backtracking algorithms. This is called as the state space tree organization of the solution space. In fact, this tree is called as the state space tree. Let's look at the structure of this state space tree. The root node defines the initial configuration of the board. The initial configuration of the board is the one on which no queens are placed. So this root node corresponds to the empty configuration of the chessboard. Now, this root node is defined to be at level 1. The level k is equal to 1. Now, at a node which is at level k equal to 1, we explore what are the different possible values of xk. Xk means here x1. So the first queen can be placed in one of the 4 columns in the first row. So this node will have 4 possible children: x1 equal to 1, x1 equal to 2, x1 equal to 3, and x1 equal to 4. The first queen can be placed either in the first column, either in the second column, or third column, or fourth column. So this node, which is numbered as 2, is a result of the problem state which we arrive after placing the first queen in the first column of the first row. So each node defines a problem state, what we reach after placing a queen. This node corresponds to the problem state arrived after placing the first queen in the second column of the first row. Similarly, this node represents the configuration where the first queen is placed in the third column of the first row. And of course, this node represents the problem state resulting from placing the first queen in the fourth column of the first row. Now, consider the nodes at level 2. The nodes at level 2 are the result of choosing the value of x1. That is, the nodes at level k are the result of choosing the value for xk minus 1. Now, at level 2, this node is at level 2. At level 2, we explore all possible values of x2 and build the nodes corresponding to the values of x2. So x2 can possibly take the values of once again 1, 2, 3, 4. But however, in this tree, the value corresponding to x2 equal to 1 is not shown. The reason is pretty obvious. The first queen is already placed in the first column of the first row. So the second queen cannot be placed in the first column of the second row because the 2 queens will be under attack. So it's trivial to say that x2 cannot have the value of 1. So that's the reason why the possibility of x2 equal to 1 is not shown in this tree, and we start from x2 equal to 2, which results in this node 3. x2 equal to 3 results in node 8. x2 equal to 4 results in node 13. So we realize that the node 3 is a result of placement of the queens 1 and 2 in positions x1 equal to 1 and x2 equal to 2. So 3 represents a problem state where the first queen is placed in the first row of the first column of the first row and the second column of the second row. Now let's look at node 8. Node 8 represents the problem state where the first queen is placed in the first column of the first row and the second queen is placed in the third column of the second row. And similarly, node 13 represents the problem state where x1 equal to 1 and x2 equal to 4. The second queen is placed in the fourth column of the second row. From this, we conclude that each node in this state space tree represents a problem state resulting from placement of queens corresponding to that level. For example, this node 54 corresponds to x1 equal to 4, x2 equal to 1, and x3 equal to 3, which means that the first queen is placed in the fourth column of the first row, the second queen is placed in the first column of the second row, and the third queen is placed in the third column of the third row. And of course, these leaf nodes represent the all possible tuples of the solution space. For example, if you look at node 12, it corresponds to the 4 tuple x1 equal to 1, x2 equal to 3, x3 equal to 4, and x4 equal to 2. Similarly, if you look at the leaf node 60, it corresponds to the 4 tuple x1 equal to 4, x2 equal to 2, x3 equal to 3, and x4 equal to 1. So this organization is called as the state space tree. Of course, the name is very apt. This represents the solution space, hence the word space, and it represents all the possible states that result from a particular configuration of the solution. So it represents the states that are possible that arise after placing the queens at each level, and it represents the space of the solution, all the solutions, and hence it is called as the state space tree. So we conclude that there are two possible representations of the solution space. One is the list representation and another is the tree representation. The tree representation is more amenable for backtracking, and this tree is called as the state space tree. So far we have seen different aspects related to the solution space, because we said backtracking is normally used to solve problems with a large solution space. So we have seen how is the solution space represented and how to enumerate the size of the solution space in case of 8 queens problem, which is an instance of n queens problem. We also said that backtracking is used to solve problems that implicitly satisfy some constraints. Now, let us try to formalize what are the constraints in the n queens problem. Now, as we know, n queens problem says that no two queens should be attacking each other, or no two queens should be under attack. So, if no two queens are to be under attack, then there are two constraints to be solved. Of course, three constraints are to be solved, but the first constraint is trivial because we say that each queen is placed in a different row. So because each queen is placed in a different row, we can ignore the constraint that two queens cannot be in the same row, because by default we develop the solution of the problem by assuming that each queen is placed in a different row. So what are the remaining constraints to be satisfied then? The first constraint to be satisfied is no two queens should be in the same column. So if no two queens are to be in the same column, xi should not be equal to xj, because we have already defined the notation. Xi represents the column in which the ith queen is placed in the ith row. Xj represents the column number in which the jth queen is placed in row j. So the column constraint demands that xi should not be equal to xj. Let's see the more typical diagonal characteristic, because no two queens should be in the same diagonal if they are not to be under attack. How to identify that the two queens are in the same diagonal or not? The idea is very simple. We said xi represents the column in which
the ith queen is placed in the ith row, and xj is the column in which the jth queen is placed in the jth row. From the diagram, we find that every diagonal position has a characteristic that the row difference is equal to the column difference. For example, consider I equal to 3 and j equal to 7. Third queen and the seventh queen are being considered. The row difference hence is 4 because the third queen is placed in the third row, seventh queen is placed in the seventh row. The row difference is 7 minus 3, 4. We consider absolute difference. Now xi, that is x3, is equal to 1, and xj, that is x7, is equal to 5. So if you look at the column difference, that is xi difference xj, absolute difference of xi and xj, you see that that's 5 minus 1 is equal to 4. So if the row difference is equal to the column difference, then we can identify easily that both the queens are in the same diagonal. In fact, this is another example where x2 equal to 6 and x4 equal to 8. So x2 minus x4, 4 minus 2, absolute difference is 2, and x2 is 6 and x4 is 8. So the difference between x2 and x4 is 6 minus 8. The absolute difference is 2. And once again, both these queens are in the same column. So if the column constraint is to be satisfied, then modulus of I minus j should not be equal to modulus of xi minus xj. Or in other words, the absolute value of I minus j should not be equal to the absolute value of xi minus xj. Remember, I and j represent the row numbers or the queens. xi and xj represents the columns in which the queen I is placed in the ith row and queen j is placed in the jth row. So xi, xj represents the column numbers and I and j represents the row numbers, and we find the row difference and the column difference, and if they are not equal, then we claim that two queens are not under attack because two queens are not in the same diagonal. So these are the two constraints which are referred as column constraints and diagonal constraints. Now let's look at some formalism related to these constraints. We find that xi can only take on particular set of values. In 8 queen problem, for example, xi can have only the values of 1 to 8 because there are only 8 columns. Xi represents the columns in which the ith queen is placed in the ith row. Similarly, in the 4 queen problem, xi can only take on the values of 1, 2, 3, 4. So this constraint that xi can take on only a particular set of values is called as the explicit constraint. In any problem, the values that the variable xi can take on is called as explicit constraint. The limitation or the constraint that is present on the values that can be taken up by xi is called as explicit constraint. And next, the other constraint is what is the relationship to be satisfied by any two values xi and xj. The first one is what values can xi can assume, and the second one what we are now talking about is the relationship between two values xi and xj. For example, in case of n queens problem, two values xi and xj should be such that xi should not be equal to xj and absolute difference of I and j should not be equal to the absolute difference of xi and xj. This is defined as implicit constraint.
It's implicit constraint because this constraint is defined by the problem statement itself. So, in the constraints, what we come across while solving the problems with backtracking can always be classified as explicit constraints and implicit constraints. We end the first part of the lecture here. Thank you.